Hey guys, so let's talk about moment of inertia. So this is a common question which comes up in a lot of interviews for engineering students especially, is what is moment of inertia? And I've asked many people or many of my friends, many of my juniors, like what is moment of inertia? And they all have this puzzled look on their face. I'm not really sure, maybe it is something integral, something that, something this, something that. So I decided, okay, let's for my friends and for everybody who out there who don't know what really exactly moment of inertia means in simple words. We are not looking for the mathematical derivation here. We're thinking of in simple terms what is moment of inertia. So let's get into it. So moment of inertia is nothing but the first thing that anybody asks you what is moment of inertia, you gotta say it is the resistance to rotate. Simple. That's the basic definition of what is moment of inertia. It is the resistance of a body to rotation. So let us understand this with an example. If you remember in the class 12th textbooks, there's this question of a ballerina and she's dancing and rotating. And they say if she puts her hands out, she rotates slowly, but when as she starts putting her hands inward, that her hands go inward, she starts spinning faster. Her angular rotation becomes faster. So why does that happen? Why does when her hands go outward, she rotates slowly, and when her hands come inward, she rotates fast? It's we can always tell it in different ways and different methods, but I like to go with a mathematical approach towards it. So let's see the mathematics behind it. So consider a disk, a normal disk with a center O. Let's say it is rotating with an angular velocity of omega. Simple, it's just rotating. And let's consider a small particle over here. Small particle, doesn't have to be a huge particle, with its mass mi and its radius from the center as ri, right? Okay, so now let's see this particles. You see this particle right here. What would be the kinetic energy of that particle? We all know it is half into mass into velocity squared. Easy, that's a pretty simple formula. We have mi for that small particle, vi. We know from circular dynamics, mechanics, I'm sorry, not even dynamics, mechanics, that the velocity is equal to r times omega, where omega is the angular velocity. Angular velocity. So let's go replacing over here. This becomes half mi r square omega square, right? Let's say ri, and omega is always constant, so that's why we like to write it always in omega terms. So let me say omega square by 2 into mi r square. This is the kinetic energy of the single particle. Now what do? Let's take the summation of all particles. You remember this cube? Let's say the whole cube. The general method is to integrate. Let's say we take a summation. The kinetic energy of the whole body would be omega square by 2 into a summation of mi ri square. This term scientists realize repeats a lot. They named this as moment of inertia. So if we had to define it, so let's say I, the moment of inertia, is equal to the summations of the mass and summation of product of mass and the distance squared. So if you remember, we have this famous formula I equal to mr squared, right? This many engineering students and many students understand very easily. Now what is the significance of this? There's a lecture of Walter Lewin from MIT who's done it very well. He's shown the significance of how this makes. Let me give you a small example with my own understanding. So let's see, I equals mr squared, right? So if I increase the radius, the moment of inertia should increase, hence increasing the resistance to rotate. So what is exactly happening here? When the dancer or the ballerina is rotating, her hands are nothing but, let's say, a concentrated mass. The further the mass is going away from the body, the R is increasing. This is the mass. Her hands, let's say her hands. The I is increasing automatically. So the resistance to rotation increases. So as she moves her hand away from her body, she starts to rotate slowly. But the moment what happens is, let's say we bring the mass close to the body. What happens right there is the M is coming closer, it means the R is decreasing, so the I will decrease. So there is no resistance to rotation. The resistance to rotation is reducing over here. That is the reason we like to bring the concentrated masses as close to the center of gravity. In simple terms, a simple example you can see in nature is, you have metro rails, right? Metro trains in cities. Someone may ask you, the support beams, why aren't the support beams in rectangular shape? We have the support beams, right? Why aren't the support beams in rectangular shapes? If you observe, they are all in a particular I section. They're all in I section. Why are they in I section and why are they not in a rectangular? Because I section has a higher value of moment of inertia, so the rotation is less, so its resistance to rotation is more. So it will not deviate when how much of a load you put on it. It will not twist, there's no turning, nothing is happening. So in simple terms, anytime an interviewer asks you what is moment of inertia, you may just go ahead and say, sir, it is the resistance to rotation. Anyway guys, thank you for listening, and I hope this cleared a little bit of doubts. I hope you can subscribe to the channel. I would like to improve on the content I can put out. I would give out topics like this which people don't really have easy clarity on it, and the videos online are pretty confusing. I'm not going to give derivations, I'm not going to do anything. I'm going to keep it simple as that. Thank you.